This screencast is about understanding the real number system and then using it to be able to rewrite and evaluate expressions. So the real number system can be organized as a series of Venn diagrams. You'll recall Venn diagrams are ways we can illustrate how sets are related. So the big ellipse here in the Venn diagram is, we'll call the real number system. Now there is a number system outside this with imaginary numbers, but we're only going to deal with real numbers here. So this large grouping is the real number system, this blue ellipse. Inside it, all the other subsets. And so real numbers can be broken up into two sets. The rational numbers, word ratio is underlined. If it can be written as a ratio of two numbers, it is a rational number. If it cannot, numbers like the square root of 2 and pi vary significantly, or e, those are irrational numbers. They cannot be written as a ratio. So irrational numbers really can't be broken up beyond that. So they are just a very big family. Now, it's bigger than that ellipse would suggest. There are a vast number of irrational numbers, in fact, an infinite number. So we have the rational numbers like 7 over 3, like 1 over 2, any ratio of two numbers. As a subset of the rational number set, we have integers, are numbers that can be written as that same number over 1 or indeed do not need a fractional denominator. As subsets of the integers, we have the whole and natural numbers. Now, the only difference between whole and natural numbers, they're all numbers either including 0 or greater than 0 that are integers as well. And natural numbers are sometimes called the counting numbers. We can count them on our fingers, 1, 2, 3, 4, 5, and so on. The whole number set is slightly greater. It includes the number 0. The natural or counting numbers do not. Integers include all of those, plus the negative numbers that do not have a fractional denominator. And in total, all of these subsets make up the real number system. Also, you're going to come across letters that define these sets of numbers. One of the big ones is R for the real numbers. You'll also see Q for the rational numbers, and some people ask why Q. It's because of the quotient or ratio involved. And then you'll see Z for integers. And the Z actually stands for the German word Zahlen, which means numbers. Let's go ahead and take a look at some of the properties of real numbers. We're going to focus on two types of properties. First, the addition properties of real numbers and the multiplication properties of real numbers, all that apply to the real number set that we just looked at. So first we'll look at the commutative properties. And sometimes it's hard to keep track of these. I look at commutative as like commuting to school. You go back and forth to school. You're changing the order. Home, school, school, home, you're commuting. So for addition, that means A plus B, two numbers A and B added together, are the same as B plus A. We've just changed the order in which they appear. The same thing is true for multiplication of real numbers using the commutative property of multiplication. A times B is equal to B times A. The associative property is where we change the groupings or the association of the numbers. So if we have three numbers, for example, A, B, and C, three real numbers, A plus B together plus that third number C is the same as A plus the other two numbers B plus C together. The same is true for multiplication, the associative property of multiplication. A times B times that third number C is equal to A times B times C. In other words, we're changing the groupings. The identity property seems very trivial at first, but it turns out to be very crucial, especially when we go to solving algebraic equations. For addition, the identity is 0. The identity property is essentially the number that doesn't change the number when that operation occurs. So for addition, if we take a number A and add 0 to it, we get A. We have not changed the number A. For multiplication, of course, if we were to use 0, we would actually turn the number into 0. So 1 actually is the number, the identity property of multiplication that we use. So A times 1 is equal to A. If we multiply a number by 1, we do not change that number. And The inverse operations turn out to be very crucial because as we begin to solve algebraic equations and inequalities by undoing operations, we need these inverse properties. For addition, the inverse is the negative of that number. So if we have a number a and we add a negative a to it, we wind up with the identity number of 0. We have canceled in that number a out effectively. For multiplication, we actually have to multiply by the reciprocal. If we have a number a, we multiply it by its reciprocal 1 over a. We get that identity for multiplication, which is 1. These are crucial because this is how we're going to help solve algebraic equations and inequalities. Something you may not have heard of before is called closure. If the operation occurs, we still restrict the result to that type of number. In this case, closure property of addition means that a plus b results in a real number. In other words, I add two real numbers and I get a real number. That always works for addition. It works for multiplication as well. A times b results in a real number if a and b are real numbers. Now, finally, the distributive property, and I like to think of distribution as sort of like handing out papers. You distribute them, okay? If we take a number a and multiply it by b plus c, the result is a times b plus a times c, which helps us enormously in simplifying. We're distributing that a over to the b, and then over to the c. Examples. First of all, name the sets of numbers to which the square root of 6 belongs. Now, it's important to note that just like you are a member of a family, which is a member of a community, which is a member of a county, a city, a state, a country, you belong to many sets, so do numbers. The square root of 6, in fact, belongs to both the irrational number set and, as a bigger family, the real number set. So let's look at the sets to which the number 5 belongs. Okay, so 5 belongs to a lot of different numbers because it belongs to the natural numbers, which are counting numbers. It belongs to the whole numbers as well. They are both subsets of integers, the integer family. 5 is also an integer. 5 is a rational number. Now, you may not think it is, but 5 can be written as 5 over 1. So that does make it a ratio or a rational number. And then finally, in the biggest group, it belongs to the real number system. Let's look at negative 2/3. Negative 2/3 belongs to the rational number set because it is a ratio itself, and of course it belongs to the real numbers as well. It's not an integer or any subset of integers because it cannot be written over 1. Okay, let's find the additive inverse and multiplicative inverse for negative 7. So the additive inverse for negative 7 is actually positive 7 because it's the number we take negative 7 and combine with through addition to get 0. So negative 7 plus 7 is equal to 0. So the additive inverse of negative 7 is 7. Now, from a multiplication standpoint, the multiplicative inverse of negative 7 is negative 1 over 7 because it's the number we're going to multiply negative 7 by to get 1. And of course, a negative times a negative is a positive. That gives us the positive of the 1. And then multiplying negative 7 by its reciprocal, negative 1 over 7, will cause the 7's to cancel out and give us 1. Therefore, the multiplicative inverse of negative 7 is negative 1/7. This screencast discussed the real number system's organization and properties of addition and multiplication under the real number system to allow us to use those properties in solving equations and inequalities.